this is a recording for math analysis, and this is section 1.3, part 2. And we're looking at continuity and behavior and limits. And I do want to just go back to the previous problem just a moment. And I did have a graph here, so I want to maybe see if I can find it out under some other things. And I just want you to notice that when we looked at if this is continuous at 1, notice if I tried to trace this with my pencil all the way from left to right, notice that I'm going down here to negative infinity, and then I have to kind of pick my pen up and kind of go back up here. And so at that line, which would be an asymptote, and maybe you've had some work with that earlier in math classes, and at that asymptote, notice that it's going to positive infinity here, negative infinity there. And so that can help you kind of think about the fact that this is infinite discontinuity as we go. And I just kind of remembered that I hadn't showed you, that graph, so I just wanted to show you that as well. Now, moving on, we're going to look at problem 2b, and it's kind of the same type of situation. We're going to go through that same process of testing that as we go. And so for this one, we'll say this is 2b, and f of x is x minus 2 over x squared minus 4. And so as we're looking at that, we want to look at if it's continuous at x equals 2. X equals 2, I'll just write there. So take a minute, put this in y equals of your calculator. And I have to say, right now I'm using a computer that doesn't have the graphing calculator on it, so I'm not going to be doing this with you, but I will tell you I have some numbers here, and I will just kind of look at that as we go. And so take a minute, put that in your calculator, pause this, put that in your calculator, and just see what the value is at 2 right. And so hopefully you got that done and you noticed that it is undefined. So this is kind of step 1 of this process, and that is to find f of 2 if it exists. And in this case, and I can kind of do that in my head, 2 minus 2 is 0. 2 squared is 4 minus 4 is 0. So this is undefined. Because we're not allowed to divide by 0. So really, immediately, I know it's not going to be continuous. But let's kind of see what happens with our discontinuity and what kind it is here. So I'm just going to write f of 2 does not exist. And so that was our first step. So we continue on. And so the next thing we want to do is look at the limit of f of x as x goes to 2. And in this case, I'm going to make a table again. And right in the middle, kind of, I'm going to put my 2. And we know that's undefined, but we almost don't care about that much. And we want to look at things to the left and right of 2 that are very, very close. So super close, I'm going to go 1.999. Less close, but very close, I'm going to go 1.99. And then here I'm going to go 1.9. And then same thing with 2. I'm going to go 2.001, 2.01, and 2.1. And you should have this in your calculator. And so take a moment and see what you get for that. And now let's see, I get 0.2564, 0.2506, 0.2501, and then in the other direction, I get 0.2499, 0.2494, and 0.2435. 0.39. Now, what we want to do is we want to say what happens as things get closer to 2 from both the left and the right. So if I'm on the left side and I'm getting closer to 2, that's what's happening with x. X goes to 2. Well, what's happening to those y values? And you know, if you want to look even closer, 1.99999, and see what happens, well, it looks like this is going closer. F of x goes to, it looks like it's going to 0.25, because look at the other side as well, to 0.25. And then same thing for this one. As x goes to 2, x goes to 2 from the positive side. F of x, well, look, it's 0.243, 0.249, 0.2499. So F of x seems to be goes to 0.25. I should have put the 0 in front of there. I will just slip it in there. So that means that it's trying to get to 0.25, it looks like. So this does have a limit. So the limit of f of x, this is for part 2, as x goes to 2, is equal to approximately 0.25. And I'll say or 1/4. So the limit does exist for this one, but the function isn't defined at that value. So think about what our choices are for types of discontinuity. If it was infinite, these y values would be going to either positive or negative infinity. If it was jump, that would mean like maybe these are going to 0.25 and these are going to like 7 or something, I don't know. And if it were removable, oh, maybe that's what it is. If it's removable, it seems like it's going to 0.25 and it seems like it's going to 0.25, but then it was not defined right there as we go. So as we look at these, we're going to say for step 3, and let me go back to my other color here. For step 3, we're going to say that the limit exists and it's 1/4, but the function is not defined at that point. So it is discontinuous. The limit, we'll just kind of justify it as we go. The limit exists, but the function is not defined. The function is not defined at x equals 2, and it has removable discontinuity, and it has removable discontinuity. And so that's what's kind of happening in that problem as we look at that. And I might have, a graph here. So sometimes I kind of have covered up these graphs so I have space. Now, here's the deal. You can't actually see this discontinuity, but actually what you should try on your calculator, there's a little hole right there, and a hole in the graph as we look at it. So what you might try doing is really zoom in with your graphing calculator and see if you can see that has a little hole in it as you go. And that can kind of help you understand that type of discontinuity. Now, the next thing we're going to look at in this part is the intermediate value theorem. And this is for continuous functions. If a function is continuous, you can approximate the location of its zeros by using the intermediate value theorem. And its corollary, the location principle. So the intermediate value theorem states that if f of x is a continuous function and a is less than b, and there is a value n such that n is between f of a and f of b, then there is a number C such that A is less than C, which is less than B, and f of C equals N. And that sounds a lot more confusing than it really is. But you do want to write some things about that. And we also want to know this location principle. So the location principle says same thing really, but now we are interested in where we might find a zero for this function. So this says if f of x is a continuous function and f of a and f of b have opposite signs, then there exists at least one value c such that a is less than c, which is less than b, and f of c equals 0. That is, there is a 0 between a and b. And so what that means is if we are looking at a table of values, so to speak, and we'll just say there's 1, 2, 3, and 4, and then let's say this is -6, -4, 3, and then 5. Well, when you look at that, if this is representing a continuous function, I have no idea. I just made those up as we go. But since y is negative here and positive there, then it has to cross the x-axis between x equals 2 and x equals 3. And so that would be a 0. There's a 0 between x equals 2 and x equals 3. Oops, x equals 3. X equals 3. So that's kind of how we can use a graph to kind of help us as we go with a problem like that. And so I'd like to maybe try to get in just one little example. So it says determine between which consecutive integers the real zeros of f of x equals x squared minus x minus 3/4 are located in the interval from -2 to 2. And so for 3a, write down that f of x equals x squared minus x minus 3/4, and take a moment, and we want to look in the interval, our interval, just from -2, including -2, to +2, including +2. So take a minute and put that in y equals and make a table of values. We just care about -2, -1, 0, 1, and 2. Find those values and see if you can determine between which two there's going to be a 0. Now let's check our work. So when I put those in, the values that I get here are 5.25, 1.25, -0.75, -0.75, and 1.25. So our job is to say between which consecutive integers are the real zeros. So lucky for us, we're not actually finding the real zeros. We're just saying between what two numbers. So it's positive here and it's negative there. So there's a 0 between those two. And then it's still negative, so it's just negative. And then it's negative here. And it's, maybe I'll use a different color just a sec. It's negative here and then positive here. So there's going to be a 0 in between those. So when we write that, we'll write it in interval notation. So there's going to be a 0 in between -1 and 0. So -1 is less than x, which is less than 0. And that's for this one. And then our other one is going to be 1 is less than x, which is less than 2. And that's going to be for that 0. So we'll say, we'll make this a statement. There are zeros on the intervals. -1 is less than x, which is less than 0, comma, and 1 is less than x, which is less than 2. So take a moment and try this problem. See if you can do that same thing, and then we'll look at that the next time. And so have a good rest of your day, and that concludes this part of the notes.